So I noticed there's been a little bit of confusion on which neutron activation analysis equation to use, and sort of the physical meaning behind neutron activation analysis and what's actually happening in each of those terms, and why we can use the comparative method and how the comparative method works. So I wanted to just briefly go through a little bit of the physical understanding of what's actually going on during NAA and why we can use a comparative method for our problem. So what we're doing is we're taking 4 different samples that we care about, a standard material that has a known concentration of elements that was prepared by Dr. Landsberger. And that's, if you look on his Excel sheet, that's going to be the numbers with the red values next to them. That's our standard. We're going to take 2 NIST standards, which are oyster and fly ash, and we're going to irradiate them and treat them like they were a sample and do an analysis on them like they were a sample. But since we already know the concentrations, we can check our answers, which we couldn't do with our unknown sample. So it's a form of quality control to say, we use this method, we calculated these concentrations, they were accurate with the literature values, we use the same method on our sample, so we know it's accurate. So it's just quality control. It's to give you a little bit of practice before you before you do it on a sample where you can't actually know if that's the answer or not, because that's the whole point of irradiating the sample. So we put all 4 of these samples in the reactor and we bombard them with a neutron flux. So if you excuse my poor drawings, if we assume that this circle is a cubic centimeter of our sample, composed of 2 elements, brown elements and black elements, with the black element containing 2 isotopes, hollow black isotopes and solid black isotopes, we can get a little bit of a picture on what's actually going on. So NAA works by an isotope of interest, which I'm going to call a parent isotope, absorbs a neutron, and through the absorption of the neutron increases its mass number by 1 and becomes the daughter isotope. The daughter isotope is radioactive and will decay with some half-life. So we're going to just focus on the first 3 terms in the large neutron activation analysis equation, the N sigma phi, which is equal to reaction rate. That's pretty much the standard equation in nuclear engineering for reaction rate. How many of our atoms are absorbing a neutron per unit volume per second? So the way we would increase that is if we say these blue kind of moving things are our neutrons. If we increase our flux, the magnitude of our flux, we will get an increased reaction rate. If we have a larger cross-section, which I kind of outline with these red circles, so the cross-section is the microscopic cross-section. It's related to the probability that a neutron will interact with a target isotope given a certain target isotope and given a certain speed of the neutron. So it's a function of speed and what it's actually seeing, what isotope it belongs to. So if we increase the cross-section, we will see a greater reaction rate because you're more likely to have interactions with higher cross-sections. So the third way we can increase the reaction rate is by increasing the number density, which is N, so atoms per cc, atoms per cubic centimeter, of the isotope of interest. So in this case, our isotope of interest is the hollow black atoms, which would be the black element. So why is it that that's the reaction rate equation and we've set it equal to activity? That's a little bit of the crux of the whole neutron activation analysis problem, is if you irradiate these samples for an infinitely long time, you will reach an equilibrium point where the rate at which parent isotopes absorb neutrons and become daughter isotopes is equal to the rate at which daughter isotopes are radioactively decaying. So you can relate the reaction rate to the activity that way, and that's how we're going to solve for our concentration down the line. So obviously we didn't irradiate these samples for an infinitely long time, so we need to introduce our first correction factor. So now we're looking at the first 4 terms of our large neutron activation analysis equation, which is the saturation correction factor. So because we didn't irradiate for an infinitely long time, we didn't reach saturation activity, and the ratio that we missed saturation activity by is equal to 1 minus e to the negative lambda ti. So if you want to accept that equation at face value, that's fine. Alternatively, you could set up the reaction rate equation and a decay equation. There should be differential equations, couple them, solve them, and you'll get the analytic solution for the saturation activity and the saturation coefficient. So you can see in this chart or in the graph, if we put time on the x-axis and we put the activity of the daughter isotope, which is really what we're interested in measuring, right? Because we're going to find the activity, we're going to measure the activity of the daughter isotope and use that to determine how much of our parent isotope must have been in that sample. And if we know how much of the parent isotope was in the sample and what percent of the element comprises that isotope, or what percent that isotope comprises the element, so that isotopic fraction of that isotope, then we can say how much of that element was in our sample. So it's kind of a working backwards kind of thing. Anyway, so we irradiate to some time, Ti, time of radiation, and then we can plug that Ti into the saturation coefficient to find our saturation coefficient and our activity immediately after radiation. So if we were to take the sample out and count it, right away with no time delay, then we wouldn't have to worry about the wait time. But we didn't count our samples right away. We let them, cool. We let the fast products kind of die away because we're only interested in our slow neutron activation, or our slowly decaying, long-lived neutron activation analysis products, because that's what this course is focused on. So we do need to correct for how much of our activity decayed away through just natural radioactive decay before we got a chance to count it. So that's this green line. So it starts at Ti. The green line starts at Ti because that's where we stopped irradiating. That's where we stopped producing more daughter isotope, and we're solely decaying now. So all we're doing is we're decaying daughter isotope. So we need a decay factor, and that's just your standard decay equation, your typical radioactive decay equation, E equals negative lambda T, where T is the wait time. So it's the time, and in the values that Dr. Landsberger gave in his Excel sheet, it's the time between when we stopped irradiating and when we started counting. That delta T is your TW. So you'll use that in your decay coefficient to find that activity. And what we're really trying to solve for in this problem is the activity of our daughter isotope the moment we put it on our detector. So that's the critical value that we're really looking for. And that's what all of these coefficients, really, the S, D, and the C, are correcting for in the first place. So it gets a little bit more complicated if we're not using long-lived isotopes, or if we're counting for a very long time. So if we can assume that our activity is constant while we're counting, then our counts is just, our activity is just the counts divided by time, right? So, counts is counts, and activity is counts per second. So if we divide counts by the amount of time that we counted, we get, a counts per second. And if it's constant, great, that's all we have to do. But we have to check to make sure that our activity is actually constant throughout the entire counting time. So the easiest way to do that is to start from this kind of middle green point right here. So we just found the activity using the decay coefficient. That's what this kind of equation is right here. So we just found this activity. We need to calculate the activity at the end of our counting time, which is right here. So we're going to use that by using the counting time and doing another kind of decay coefficient. So it's going to be another e to the lambda t, and we're going to see what that value is. If it turns out that and we're going to do an example at the end just to kind of make sure everyone's got the gist of it. But if it turns out that we didn't really lose much activity as we were counting, then go ahead and treat it as a constant activity and just counts divided by time is your count rate. That's fine. But if you have kind of a short-lived activity, or if you counted for a long time, because some of the samples were counted for a pretty long time, you might have to integrate in order to find the activity of the sample when you placed it on the detector. So again, we're looking for the critical value that we're looking for is the activity when we placed it on the detector, this kind of central green point right here. So the way that you would do that is you would integrate with respect to time, where activity is a function of time, and the function of time would be the initial activity. So the initial activity being the activity when you place it on the detector that we're trying to solve for. e to the negative lambda t, right? So it's decaying. Once we put it on the detector, it's decaying. That's kind of all this equation's saying, and we're integrating over time to get the total counts. But we measured the total counts. We didn't measure the initial activity, so we have to resolve this equation and put, multiply by lambda, divide by 1 minus e to the negative lambda over tc, and solve it for a0, where a0 is the activity when we placed our sample on the detector. So for some people, the activity at the end is the activity at the beginning, but if you do that check and activity wasn't constant, then you have to make this correction. So keep in mind that the c here is not the c coefficient. So the c coefficient is this 1 minus e to the negative lambda tc. It's kind of buried in this equation. Don't let that distract you. C here is net counts. So we've covered the first 6 terms of the neutron activation analysis equation. What are these other 3 terms? The theta there is actually, we're going to embed it in this atom density. So this would normally be atoms per cc. We're going to just convert that to atoms, total atoms. So we're going to take the isotopic fraction, so the percent of our isotopes of each element. So say iron 56 is 50% of all iron, then this value would be 50%. It's not, it's something else, but hypothetically, let's say that's true. P gamma in this, I honestly have no idea what letter that is. I'm just going to call it squiggle, I guess. Are functions of our measurements. So when we take our daughter isotope, which is this kind of black atom, it's going to give off gamma radiation, which will have different but characteristic energies, a lot like electron orbitals. It's almost exactly the same process, except it happens in the nucleus with nucleus energy structures or energy levels, and transitioning between the two gives off characteristic gamma rays. So a specific energy of gamma ray may not be emitted every single time a daughter nucleus decays, so we take that into account using the fraction. So P gamma is the probability that when that atom decays, it will give off a gamma ray with this specific energy. So we only measured one energy for each element. So we were looking at a peak with a certain, when we were looking at the count rates in the germanium detector, we were looking at a specific energy peak. So the efficiency of our detector is going to be related to the energy at that peak, but we're not going to have to worry about that because we're going to use a comparative method. But that's kind of what that squiggle term is the efficiency of the energy of that gamma ray in our detector. Also, the gamma ray energy is going to be emitted isotropically from our sample, so in all directions evenly. We don't have 4 pi geometry on our gamma ray detectors, so some of those gamma rays are going to escape to the room and not interact with our detector at all. So we have an efficiency that normally you would do an efficiency curve and efficiency calibration. I think there was a lab earlier in the semester on that. You could probably just look through the literature on it for more information about gamma ray detector efficiency. All right, so now that's every term in the full-blown neutron activation analysis equation. Why is it that we're not using that equation? And the answer is because it's big and complicated, and we don't have to. So if we adjust the atom density, which is that N term, we can take into account the isotopic fraction. So what we're really interested in finding is the concentration of the element in our sample. So we can set up an equation that solves for the concentration in parts per million, which there's a factor of 1e to the negative 6. I didn't include that in here. Do include it in your spreadsheet. This equation as it's given will give you absolute fraction, so you'll have to multiply that by 1e to the 6 to get the parts per million, because it's per million. Anyway, but we're going to take the N. I guess the comparative method is to take the total neutron activation analysis equation that we've already defined in the last couple slides for an unknown sample and divide it by the same big neutron activation analysis equation for a known sample. So by dividing it, we're taking ratios of the two terms, so a lot of things start to cancel out. So you can look at that. I mean, I did that in this equation right here. We took the activity of our unknown sample. This is the neutron activation analysis equation. Keep in mind this chi should be the squiggle. I forgot what its name was, so I didn't put in the right letter. And by doing the ratios, we're going to see things start to cancel out. So we're using the same reactor, so our fees are going to cancel out, right? Because the flux is what the flux is. We use the reactor at the same power. A lot of these samples were radiated together. It's the same. That ratio is 1. Same with our detector. We had the detector in the same geometry. We were looking at the same energy gamma ray. So our P gamma and our efficiency for our detector are the same. Our ins, our atom compositions, we're going to end up subbing in our, this equation. We're gonna solve the two ratios, n over ns, n over ns, set them equal to each other, and solve for x, which is what you end up getting down here. And then our cross sections are going to disappear, or the ratio of the two is going to be 1 because our flux is the same. The energy distribution of the flux is the same. So our cross section as a function of energy isn't really, it's not really affected. And we're looking at the same isotope, and cross section is a function of energy and isotope. So since those are both the same, our cross section is the same. So you can just, that ratio is 1 also, we can remove it. So if we set our n ratios equal to each other, and we solve this equation for the n ratios and set those equations equal to each other, we can then solve for the concentration of our isotope of interest, or the concentration of our element of interest, excuse me, using this equation where this is the activity. S is always for standard, by the way. I don't know if I made that. I don't know if I said that at the beginning or not. I always use S for standard, all the subscripts. So activity of our sample over our activity of the standard times the ratio of our saturation coefficients times the ratio of our decay coefficients times the ratio of our masses for our samples times the concentration of the sample should give you, or the concentration of the standard, excuse me, should give you the concentration of the sample in parts per million, assuming this value, the concentration of your standard, was in parts per million. So we're going to do an example very briefly together on the NIST 1566 oyster sample. So we were looking at zinc in this problem. So we took the zinc values for the standard, where the standard is those numbers with the red next to them. So we found the irradiation time, we found the wait time, we calculated our saturation coefficients based on the equations that I already mentioned in these slides. Same with the decay coefficients. And then we get to count time, and activity. And this is where you need to go back and make sure that you can treat your activity as constant during your counts, or during your measurements. So our longest count time was 10,588 seconds, and it's the same isotope, so it's the same half-life. So if I'm confident that my activity was constant for this long irradiation time, I can be confident that it's constant for the short irradiation time. So I'm only going to test the long one. So if I do the standard decay coefficient, so what I'm trying to do is compare the activity at the beginning of my count to the activity at the end of my count. And I'm going to do that by just decaying my activity, a unit worth of activity, 1 unit, for that amount of time, and see what I get. So if I had no decay, I should get 1, one at the beginning, 1 at the end. But because we're decaying, it should be slightly less than 1. So when I do this, I get e to the negative lambda t, where t is the count time, and I get 0.9996. So for me, that's good enough where I can treat my activity as constant. So I can just say counts divided by count time is counts per second. That's my activity. So 14,375 divided by 10,588 is 1.36-ish. So that's going to give me my activity, and I'm going to solve for x using this equation right here, and that gave me 760.4 parts per million. Now the answer in the NIST values in the literature is 830, so that gives us an error of 8.4%. But I believe Dr. Landsberger said it was about 4 or 5% water, so that kind of threw off the answer a little bit and gives us actually more reasonable answer. So that's not too bad. So if there's any demand for it, I can do I will do a brief walkthrough on how to do the error propagation, or the uncertainty propagation, not necessarily the error. If you guys want me to make a video on it, that's fine. But I think Dr. Landsberger's PowerPoints are pretty instructive in how to do it. But if you have any questions, just let me know.